What's going on, everyone? Welcome back to another Tutor Toby video. So in today's video we'll be going over some more complex brine tank problems because the singular brine tank problem that I did in the last one I felt wasn't quite enough, so I figured I could show some complexity of simple brine tank problems by making them a little bit more complex. So the two that we're going to be going over in this video today are non-constant flow rates, so that's where the flow in or the flow out is like dependent on time. And then we're also going to go with connected tanks. So we have flow going into one tank, and then the out of the one tank goes into a second tank, and then that flows somewhere else. All right, so let's get into it. All right, so just like last time, we'll draw our little diagram. So we have a brine tank right here with a volume V. It has a flow out, and it also has a flow in at concentration equals C. All right, so first we make the same differential equation that we did last time. So this is probably the only formula that you have to quote unquote memorize. You can always just kind of think of it to remember the formula, but if you want to memorize it, go ahead. We have our change of the amount of stuff in our tank at like an instantaneous point in time, dt, an instantaneous point in time, is going to be equal to stuff in minus stuff out. Okay? So now we say our stuff in is actually equal to our flow in times our concentration in. And then likewise, we have our stuff out is equal to flow out times concentration out. And then we know that concentration out is just equal to the concentration of the tank, which is stuff in the tank, divided by the volume of the tank. Okay, so let's just plug this in. So we have, remember, just like last time, we'll call stuff in the tank equal to an x. So then we have x prime is equal to stuff in. So stuff in is equal to flow in times concentration in minus the stuff out. So that's going to be minus flow out times concentration out, which I'll sub in right away, which is equal to x, because our stuff in our tank, divided by the volume of our tank. Cool. Okay, so now what we say is, let's say that flow in is a function of time. So flow in is a function of time. And what's like a reasonable flow in as a function of time? Well, it could be constant, so that would still technically be as a function of time, but not really that. We already went over it. So now what's another one? Well, it could be like linearly increasing, right? So our flow in could be gradually increasing. This isn't really that feasible because you can't just keep increasing your flow in. So how about we say that it's some sort of exponential function. So let's just call it like e to the negative t, right? So let's say at 0, it'll start at 1, and then it'll slowly decay until like we're like shutting off a valve, we can think of it. So it's going full blast, which is right here, and then as soon as we start to close our valve on our, garden hose or something, the rate will slowly drop to 0. Okay. So let's just say that's our flow in, and then, yeah, let's just solve for this one. So we can say x prime is equal to e to the negative t minus, so what's our flow out going to be? Well, let's have our flow out also not be constant. So let's have our flow out be a function of our height. Yeah, that makes sense. Let's have it be a function of our height, where the height is going to be the water height. So obviously, if I'm at a higher water level, like this, my flow out is going to be greater than if I'm at like a, let's say, lower water level. So now it's orange water. So then this would go to like a lower flow out. Okay, so let's have it be linear with height. So let's just say flow out is equal to the height h in our tank. Okay, so how do we figure out height from volume? So we know volume, right? Because that'll be given, and I already gave it to you up here. And now, how do we figure out our height of our water? Well, that's just going to be volume equals area of the base times the height. So that means that height is going to be equal to volume divided by area. So let's say that this has a bottom area equal to A. Okay? So now we get that our flow out as a function of h is equal to h, which is just equal to v over A. Okay? And then since our flow in and our flow out aren't necessarily going to be the same, we know that our volume is actually a function of time, right? So obviously, if we don't put anything in and our water levels up here, it's going to slowly drain out. Whereas if our flow in is really fast and we kind of like plug this hole for a second right here, then the water level is obviously going to rise. Okay, so now we get our flow in, we said, is going to be this, and our flow out is going to be equal to, let's see, we already found it right here. So our flow out is volume, that's a function of t, all over my area, and then we have times my x all over my volume with respect to t. So I did not expect that. And these cancel out really easily. That's kind of cool. However, that's going to be like a little bit like easier to solve. So how about we change up here to have my flow out not be dependent on h, but how about we make it dependent on, I don't know, h to the 1/2. So still, as my water level is higher, it's going to be going out faster, but it's not going to directly depend on it. It's kind of going to slow down. As you increase more water in the tank, it's going to not have as much an effect. So like an increase right away is going to be a pretty big effect, whereas the same increase later is going to be a relatively smaller effect. Okay? So if we plug that through, we know that this is just going to go h to the 1/2. So then we have this is root a, and then we have v to the 1/2, and then we have that. There we go. So we still get some relatively nice cancellation, where this makes that into a 1/2. I'm actually just going to write it in a different line. So then we get this minus v to the 1/2. So those two cancel out, and we get x all over v of t to the 1/2 times 1 over root a. Cool. So how do we solve this equation right here? So magic of brine tank problems and the magic of integrating factor method. So this is just equal to x prime plus, let's say, 1 over root a v of t to the 1/2 times x is equal to e to the negative t. Awesome. So our integrating factor is going to be e to the integral 1 over root a v of t to the 1/2 dt. So now we know that this is our integrating factor method. I'm actually not going to solve for it quite yet. I'm just going to wait and solve it later, but I'm still going to do the same steps as we would usually do. So we multiply this to each side, so we get e integral 1 over root a v to the 1/2 dt times the group from up here. And then we have to multiply it on the other side as well. So we get this, and then we say that this is just equal to d dt of x times my integrating factor method, because the special form that this left side is in is equal to this side right here. And then to get rid of a dt, again, slap an integral on each side with respect to time. So the integral and that cancel out, so we get x. I should just copy this. So we get x times this is just equal to the integral e negative t times e to the integral 1 over root a v to the 1/2 dt dt all over, so we'll bring this to the other side, e to the integral 1 over root a v to the 1/2 dt. Cool. So now all we have to do is find out what this v is, right? So what is my v of t equal to? Well, my change in volume at an instantaneous point in time dt is going to be, it's kind of like the same as the brine tank problem, where it's going to be equal to my volume coming in minus my volume going out. All right, so what is my volume going in? Well, this is just e to the negative t. And then what is my volume going out? Well, that's the same as the flow going out, right? Because flow is a volume. And that's given right here. So it's v to the 1/2 all over root a. That equals v prime. Okay, so now we see that this is another ordinary first order ordinary differential equation. Okay, so this is actually a really kind of difficult equation to solve, because we see right here that our differential equation is non-linear, right? So it's not just like a v term, so it's not just like v to the first, it's actually v to the 1/2, and that actually makes this really, really hard to solve when it's non-separable, right? We can't separate out the t and the v, and it's non-linear. So how do we solve this problem? Well, let's use a physicist trick. So let's play physicist for a second. Let's say that our v initial is really, really large. It is much, much greater than 1. Okay, so if our v initial is much, much greater than 1, then my v prime is going to be equal to e minus t minus a really big term. So big term. Now, since I'm starting at 0, right here, this is at most 1, and it's minus a big term. So we'll just say that this is approximately just equal to my big term. So then our differential equation turns into v prime equals minus v to the 1/2 all over root a. Cool. So now we can actually solve this problem because it's separable, right? But first we should check if, so I only check this for like t equals 0 case, but we should check it for every t case. So does this does this approximation work for every point in time? So 0 all the way up to infinity. And we note yes, it actually does work. And that's because this decaying exponential term is going to decay a lot faster than this v to the 1/2 term. So our approximation is valid, and we can actually use this equation right here. So now we get dv over dt is equal to negative root v all over root a, and then we get dv all over root v is equal to negative 1 over root a dt. So we can just slap an integral on each side. So that goes to 2 times v to the positive 1/2 equals negative 1 over root a times t. And then since these are both indefinite, we'll have to add a plus c, and then our plus c is just right there. So now we get our v as a function of time is equal to negative 2 root a t plus, I'm just going to keep it as c. Technically it's this c times 2, but I'm just going to leave it as some constant. And then this is still v to the 1/2, so that means we'll need to square each side. Like this. Cool. All right, so now what is this c, right? We'll need it in order to solve our problem. So we get that from our initial conditions. So what is my v naught? So my v naught is equal to, what should I call it? 1? Okay, so my v naught is just equal to 1, which then goes to 1 is equal to c squared. C equals plus or minus 1. Okay, so is this c1 plus 1 or is it minus 1? Well, in order to figure that out, we'll plug our initial condition back into our original one before we squared each side. And then we also will start denoting this one by c1. So we actually solved here for c1 is equal to plus or minus 1. And then we'll note that my c divided by 2 is equal to c1. Okay, so plugging this into here, we get 2 times 1 is equal to 0 plus c. So c equals 2, which then goes to c1 is equal to plus 1. Awesome, so now we know that. So then we get our final solution, which is v of t is equal to negative 2 root a times t plus 1 squared. Awesome, so now we can actually plug this back into the big x of t term that we got up here. So we'll just copy that down there, and then I'll just go like this to save it for later. So then we say integral 1 over root a times this square rooted, the squared and the square root will just cancel, so we get negative 2 root a t plus 1 dt. Okay, so what is this equal to? Well, it'll be natural log of negative 2 root a times t plus 1. And then if we took the derivative of this, we would get 1 over this group right here. And then we would get a factor of negative 2 times 1 over root a. So we actually have a 1 over root a already down here. So we know that we don't need that term. So the only term we need to cancel is going to be that negative 2. So we go 1 over negative 2, and I just bring the negative to the top. Awesome. So then this is actually our exponential, right? We have to exponentiate all this for this term right here. So that is just going to be equal to e to the natural log of 2 root a t plus 1, and then all of this to the negative 1/2 power. If we remember our exponentiated power rules, we know that this would just go in front. All right, so now we know that this and this cancel out. So we can cancel out the e in the natural log. So we get our e to the integral at the dot term is just equal to 2 over root a t plus 1 to the negative 1/2. Alright, so this is getting kind of fun, or hard, and a lot of stuff to do, but we'll just keep pushing through, because I'm already this far through the video. So then we plug this back in, up here, and we get integral e negative t times 2 root a t plus 1 to the negative 1/2 dt. Alright, so what is this integral going to be equal to? So I double checked, and this would be an integral that we would have to solve numerically. So in the end, we don't even get an analytical solution, and we'll have to solve something numerically. So if we're going to solve stuff numerically, we might as well just have solved the initial differential equations numerically. So we'll go to MATLAB to show you how I did that. Okay, so now on to my MATLAB in order to numerically approximate this. So I'll initially do step sizes of 0.01, and then I want to just numerically approximate from t equals 0 to t equals 10. So I set the initial conditions to, I have an initial volume equal to 10, I have an initial A is equal to 1, and my initial concentration is just equal to 1. So we know that my x initial, so the amount of stuff that I have initial, is just equal to my volume initial times my concentration initial. And then if I run this script, so I'll just run it like this, we see that my numerical approximation of v looks like this. So my volume starts out at 10, and then it decreases pretty drastically. And then we have my numerical approximation of x is going to be my stuff in my tank is equal to that, and then it also decreases basically exactly equal to this, and that's due to my concentration coming in is just equal to 1. Cool, so that's the end of the video, guys. Thank you so much for watching. I ended up not getting to multiple brine tanks in a row because this one took a lot longer because I chose to do the change in the flow out is equal to the square root of the height instead of just the height, which would have been a really nice simplification. If you guys want, you could solve that one. It's relatively simple. Just do an integrating factor method. And thank you so much for watching. If you like this video, make sure to give it a thumbs up, comment below, subscribe if you want to. And I'll see you guys on the next video.